Welcome and thanks for tuning in. This is the presentation for Backpack, packing more into Backprop. We are presenting a software library that extends the existing backward pass in PyTorch to compute information that is not necessarily the direct derivative of a function. This includes individual gradients from a mini-batch, estimates of the noise in the form of the mini-batch gradient variance or second moment, and curvature approximations of the Hessian, like the generalized Gauss-Newton and the Fisher information matrix. One of the main points we would like to make is that the computation of most of those quantities is not necessarily expensive. Oftentimes, you just need a slightly more flexible, small modification of the existing backward pass. Sometimes, it is even possible to recycle information that is backpropagated by the auto-diff library. But it is difficult to do this in the current software environment. Using the backward pass as a black box is not enough to cheaply access those quantities. We hope that our software package enables you to spend less time on the implementation and more time on research, and that you think about what you could do if you had access to more information from the backward pass. Let's start with some examples of how information other than the gradient can be helpful to improve, say, training a neural network. Imagine you're using your optimizer of choice and it starts out making a lot of progress, but at some point the loss stagnates and does not improve anymore. One possible reason for this is that the noise caused by sampling of mini-batches is too large compared to the signal you're getting from each gradient. Monitoring the signal-to-noise ratio by estimating the variance from each mini-batch could help tune the training hyperparameters, either by increasing the batch size or decreasing the step size as the noisy regime is entered. Another example is importance sampling. When performing SGD with mini-batches, one would like to draw samples that contain a lot of information about the full gradient. The histogram on the right shows the gradient norm for each example, which is the measure of its importance. In the beginning of the optimization, all examples provide some signal, but as training proceeds, most of the samples become less informative as they are modeled correctly. In this case, the sampling procedure should focus on examples that are still wrong and provide some signal, rather than waste cycles on samples with zero gradient. Those previous examples show areas where existing algorithms that can already be run could be improved, but there are applications that need to have access to more information to work in the base case. One example of that is differential privacy. The basic idea of differential privacy is that the model should avoid leaking too much information about the examples it was trained on, so the model should not depend too heavily on individual samples. One way to achieve differential privacy is to train the network with stochastic gradient descent, but to modify the individual gradients to avoid privacy issues. This can be achieved by clipping the individual gradients, sketched in orange, up to some threshold, indicated by the dashed sphere, before taking their average and use that as a descent direction. To achieve true differential privacy, the truncated individual gradients need to be perturbed with additional noise, but the computational challenge to achieve differential privacy is accessing the individual gradients and their L2 norms. These examples illustrate the usefulness of information other than the gradient. Now, the obvious question is, why is computing those quantities so difficult? We have high-performance black boxes to do automatic differentiation provided by existing machine learning libraries. Given some data x, y, a model, and a loss function, libraries like PyTorch or TensorFlow can automatically compute the gradient from the computational graph of the forward pass. Using auto-diff as a black box, we can loop over the samples, doing a forward and a backward pass to compute individual gradients one at a time. The problem with this approach is that it's not efficient. Here's an example comparing the computation of the overall gradient in one go and the for loop approach computing individual gradients before averaging them over 50 iterations. The for loop is terribly slow, even though both approaches perform the same mathematical operations. This example only has 128 samples in a mini-batch and already loses a factor of 10 in the computation time due to less factorization on the hardware. Just by looking at the math, it's not obvious why it is so difficult. The overall gradient is the sum of the individual gradients, so the individual gradients are already computed during the backward pass, even if implicitly. The main problem is that we cannot access them directly because they are automatically aggregated, and similar problems hold for other quantities that have been asked for by the machine learning community. To address those problems, we are introducing Backpack, a software package built on top of PyTorch that can efficiently give access to quantities other than the gradient. A design goal of Backpack was to reuse existing frameworks to add only the minimum tools needed to extract some quantities useful in machine learning in an efficient way rather than create a new auto-diff library. Backpack should work out of the box with existing PyTorch code, and you can try it out with a simple pip install backpack-for-pytorch. We hope that easy access to this information with Backpack can help you in your research and stimulate new approaches based on quantities that were previously too difficult to compute. Now, let's look at how Backpack integrates with some PyTorch code for a simple image classification task. Say, you are loading your typical MNIST data, creating your model, and defining your loss function in PyTorch. You can compute the loss using a forward pass and call backward on it to invoke the automatic differentiation engine that will work out the gradient for each parameter of the model and make it accessible in the grad attribute. Let's assume you would like to compute the variance of the gradients in the mini-batch to tune the learning rate. You first have to import Backpack and tell it which part of the computational graph it needs to look at by extending the model and the loss function. Then, you can ask for the additional quantities you want by calling the backward pass inside a Backpack context using the with Backpack syntax. The variance will get stored alongside the gradient in each parameter. It is also possible to evaluate multiple quantities during a backward pass. Here's an overview of the quantities that Backpack version 1.0 gives access to in addition to the variance. As first-order information, we provide the individual gradients, and more specialized quantities like the variance, the second moment, or the L2 norm of the individual gradients, most of which we have encountered in the previous examples. Some of them could in principle be computed from individual gradients, but are optimized in Backpack to avoid storing this tensor, which scales with the model and batch size. Backpack also gives access to approximate second-order information. The full curvature information represented by the Hessian, or approximations thereof, is usually too large to store in memory. In particular, we support the exact computation of diagonal elements of the Hessian and the generalized Gauss-Newton. Moreover, we offer a cheaper approximation of the latter based on Monte Carlo sampling, which is related to the diagonal of the fissure. As a second class of memory-efficient curvature information, Backpack also supports recently proposed Kronecker factorized approximations of the fissure and generalized Gauss-Newton. Here is an impression on how Backpack performs in practice. Revisiting the example of individual gradients with a for loop, Backpack gets much closer to the performance of computing the overall gradient in one go with PyTorch. Compared to a for loop approach, there's almost no overhead. The bottom bar chart shows benchmarks on a bigger convolutional neural network with 3 convolutional and 3 dense layers on CFAR10. Most quantities add only little overhead to the computation of the overall gradient, shown in gray. The timings shown in blue here represent the time it takes to compute the overall gradient and the additional quantity. For example, computing the overall gradient and the second moment adds no overhead. Computing the individual gradients on top of the overall gradient adds only 10% overhead. Other quantities like the individual gradient L2 norms, the Monte Carlo sample generalized Gauss-Newton diagonal, and K-fac, all of which require roughly 1 additional backward pass, are obtained together with the gradient in less than 2 gradient computations. Before giving a high-level overview of Backpack's internals, we would like to briefly mention examples of other projects and showcase what can be done with automatic differentiation. PyHessian is a library that provides access to second-order information. It leverages Hessian vector products of PyTorch's automatic differentiation to compute spectral information of the Hessian. The auto-diff systems JAX, Zygote, and diffsharp in Python, Julia, and F# respectively try to improve the current state of automatic differentiation by adding new features like better support for vectorization, forward and backward automatic differentiation, and the ability to differentiate through program code like if statements and for loops. Backpack's approach is different. We are not implementing an automatic differentiation system, but extending the existing backward pass in PyTorch to compute other quantities than derivatives. Let's say you have a neural network which can be expressed as a sequence of layers. During the forward pass, each layer applies its transformation, propagating the information through the network. The network's output is used to compute the loss. Calling backward on the loss will backpropagate the partial derivatives and compute gradients according to the chain rule. Each layer will compute the derivative with respect to its input and parameters given the derivative with respect to its output. The way Backpack works is that it hooks into the backward pass and looks at the messages being propagated to extract additional information. For second-order quantities and curvature, we need to backpropagate additional quantities through the graph, but the additional computation cost is limited. As Backpack relies on the existing backward pass provided by PyTorch, the approach is not fully general, but can reuse existing implementations and add only a minimal amount of code needed to extract quantities of interest. We believe that Backpack's generality can be further improved and are actively working on increasing the library's capabilities in future releases. In summary, we have developed a software library that integrates well with PyTorch and offers efficient access to quantities that were difficult to compute before. We hope that projects like Backpack will not only help you in your research, but also inspire new directions that can make use of those quantities and lead the community to think more creatively about what can be done with automatic differentiation tools. While the main frameworks for machine learning are one of the reasons we have progressed so much as a community, there are still innovations possible in how to do and use automatic differentiation. We encourage you to give Backpack a try. You can find self-contained examples on the website and the GitHub repository. Feedback is highly appreciated. Please get in touch with us if you have any questions, feature requests, or suggestions to further improve the library. We're actively developing Backpack to make it a useful tool for the community. Thank you.